When you peel back all the layers of data, machine learning, and AI, what do you find at the very core? Probability. Today, we're going to build a solid, intuitive understanding of how it all works, starting from the absolute basics and building our way up one concept at a time.
Okay, so here's our game plan. We're going to start with the simplest possible thing, a single data point. Then we'll figure out how to assign probabilities to things. From there, we'll see how to structure data into inputs and outputs. And finally, we'll uncover some really cool ways to find relationships hidden inside that data. Let's jump in. All right, first things first. We have to start with the most fundamental concept there is. You can think of it as the single Lego brick of this entire system, a single piece of information.
And here it is. We call it a data point, or a datum, and we'll use a lowercase z to represent it. So what is z? Just think of it as one single thing we observed. The result of a coin flip landing on heads? That's a z. A customer buying a particular product? That's another z. It is the absolute, most basic building block we have. So if our little z is one Lego brick, then the sample space, which we write with a capital Z, is the whole box. It's the entire set of every single possible brick you could ever pull out. And that little bit of notation, z is in z, that's just a quick, mathy way of saying that our specific outcome, our z, belongs to that bigger universe of possibilities, z. Well, how do we get one of these data points? We perform what's called a random experiment. Now, that sounds way more complicated than it is. It's just the formal name for whatever process gives us an outcome. The act of flipping the coin, the act of rolling the die, that's the experiment. It's the action that pulls one z out of the entire sample space z. Okay, so we've got our universe of possibilities. We know all the things that could happen. But how likely is any one of them to actually happen? This, my friends, is where probability enters the picture. And you know what's great? Everything is governed by just two super simple rules. First, the probability of any outcome, P of z, has to be a number somewhere between 0 and 1. Right? It can't be negative 10% likely, and it can't be 150% likely. It's always somewhere on that scale from impossible to certain. Second, if you add up the probabilities of every single possible outcome in your sample space, the total has to be exactly 1. No more, no less. It just means we've accounted for everything. A lot of the time, we don't really care about just one specific outcome. We care about a group of outcomes. We call this an event. So back to rolling a die. The outcome rolling a 2 is a single data point, but rolling an even number, that's an event because it includes the outcomes 2, 4, and 6. And to find its probability, it's incredibly simple. You just add up the individual probabilities of all the outcomes inside that event. That's it. All right, let's get a bit more realistic. In the real world, data points aren't just these single values floating around in space. No, they usually have distinct parts that relate to each other. So let's break them down. Most of the time, we can think of our data point z as a pair. We'll call it xy. The way to think about this is that x is the input, kind of like the question, and y is the output, or the answer. So for example, x could be all the features of a house, its size, location, number of bedrooms, and y would be its final selling price. And that brings us to our cast of characters for the rest of this journey. So z is our data point, the whole x, y package. Little x is an input, and little y is an output. And just like before, the capital letters represent the whole set of possibilities. So capital X is the space of all possible inputs, and capital Y is the space of all possible outputs. It's a handy little reference. Now let's just quickly touch on some formal notation that can trip people up at first, but it's actually super helpful. We use capital letters like X, Y, and Z to talk about the idea of a random variable, basically a placeholder for a value that's going to be determined by our experiment. So when you see something like P of z equals z, all it's asking is, what's the probability that our random process, z, ends up with a specific outcome, lowercase z? It's just a cleaner way to write things down. Okay, now that our data is nicely structured into inputs and outputs, this is where things get really interesting. We can start asking much smarter questions by looking at the relationship between x and y from a few different angles. First up is what we call joint probability. I like to think of this as the God view of your data. P of x equals x, y equals y tells you the probability of a specific input x happening together with a specific output y. So what's the probability that a house is exactly 2,000 square feet and sells for exactly $500,000? The joint probability distribution map gives us the answer for every single possible combination. So, from that God view, we can slice up the data in two main ways. On one hand, you have marginal probability. Think of this as your view from the sidelines. You're only looking at one variable and asking, what's the overall probability of this output no matter what the input was? Then you have conditional probability. This is the view from inside the data. Here you're asking, okay, given that I know what the input is, now what's the probability of the output? So how do we get that marginal probability? We basically just ignore the other variable. Let's say we want the marginal probability of a specific output, y equals y. We just go to our big joint probability table and add up the probabilities for every single input x that was paired with that one output. We're summing out the x's to get the big picture view of y on its own. Now for conditional probability. The key here, and you will see this everywhere, is that vertical bar. That bar means given. So when you see p of y equals y, given that x equals x, you read it out loud as the probability of output y, given that we know the input is x. We find it by taking the joint probability of both things happening together and then dividing it by the overall probability of the input happening. We're narrowing our focus, creating a smaller universe where we know x is true, and then seeing how likely y is inside that new, smaller world. All right, let's put these tools to work. For our final step, we're going to use them to formally describe the relationship, or maybe the lack of a relationship, between our inputs and outputs, and even start making some predictions. So what happens if knowing the input gives you absolutely zero new information about the output? Well, we have a special name for that: independence. Formally, what it means is that the conditional probability of y given x is exactly the same as the plain old marginal probability of y. In simple terms, knowing x happened didn't change the odds of y happening one bit. And that's really the whole takeaway of independence. If your inputs and outputs are independent, then knowing the input is completely and totally useless for predicting the output. Think about it. If the color of a car and its top speed are independent, then me telling you the car is red gives you no help in guessing how fast it can go. Okay, let's switch gears to making predictions. The expectation is basically the average value we'd expect to see for our output if we ran our experiment over and over and over again. Now, it's not just a simple average, it's a weighted average. We calculate it by taking each possible output value y, multiplying it by its own probability, and then summing up all those little pieces. It gives us a single number that's our best guess for the long-term average. And this right here is arguably the most powerful tool we've built today: conditional expectation. This gives us the best possible prediction for our output y when we already know the input is x. The formula looks almost the same, right? But the crucial difference is we're now using the conditional probabilities. This is the logic at the heart of so many predictive models we use every single day. And there we have it. We went from one tiny little data point, z, all the way up to making specific, informed predictions with conditional expectation. We've built the entire foundation, the entire language of data science, from scratch. The framework is now yours. The real power lies in the questions you choose to ask.